You're listening to the Java Easily podcast, episode number 9.
Java Easy. News, tutorials, tips. Everything you need to know as a beginner Java developer.
Hi there, welcome back. In this episode, we're going to look at different types of Classpath and see how those work with each other. Now, first of all, before we start, if you're a complete beginner to Java and you want to get a helping hand getting set up and beginning your Java journey, then go to javaeasily.com and you can sign up for our Java Jumpstart program there. It's completely free. You can download a guide which gets you up and running in Java in the quickest way possible. If you're more experienced though, you might like to check out our courses over at courses.javaeasily.com, where we have courses on Spring, Spring Boot, JUnit, Mockito, and Java itself, along with some others too. Anyway, let's jump into the episode and look at the different types of Classpath. Okay, so first off, let's define what we mean by Classpath. So Classpath in Java is basically a set of locations where Java, and I just put Java in inverted commas for now, we'll clarify what that means in a second, but where Java can look to load the classes from that it needs to use. Specifically, these are the classes which you've used in your application code. So for example, when you do import java.util.list, you're using the list class because you've issued an import statement, so that's one way of using a class. Another way would be just to use a class name in code, for example, without the import statement. So for example, string s equals, and then in quotes, sugar, with of course a semicolon at the end. Now here you don't need to issue an import to be able to use the string class, and that's because by default, all of the classes which are in the java.lang package are implicitly imported for you into your code, without you having to give an explicit import statement like we do with import java.util.list. So list and string, these are two classes which are part of the JDK, that's the Java Development Kit. The list is part of the collections API, which is a set of classes which enable you to group and process things together into lists, sets, maps, that kind of thing. And we have string from java.lang, which is part of the standard set of classes which are implicitly imported into your application. Now, unless you're doing something super simple, just using core Java without any other libraries, or you're building a system from scratch using purely core Java because you're not allowed to use any other libraries, and that can happen. That once happened to me when I was working at Goldman Sachs, probably about 15 years ago now. We weren't allowed to use Spring or any of the enterprise stuff, so we had to pretty much write our own kind of implementations of that, or use some of the libraries which were developed in-house. But unless you're using pure core Java, you're going to want to use some other libraries for the other frameworks that you're using. For example, Spring, Spring Boot, Apache Commons, whatever else you might use. And in those circumstances, this is where the Classpath comes in. Or more specifically, this is where the Classpath appears more relevant. Ultimately, there's always a Classpath in Java whenever you compile or run a program. These are the notions of compile time and runtime classpaths, which we'll get to in a second. So you always have a classpath, but it only becomes relevant to you when you're, as a developer, when you're wanting to use these external third-party libraries. For example, if you wanted to use Commons Lang, so that's a utility library from Apache Commons, you could download that library, so that jar file, jar standing for Java archive, which is an archive, effectively a zip file of all of the classes, that is the compiled classes, the bytecode, which are included in that library, all zipped up into one zip file, which is the Commons Lang jar file. You'd want to download that onto your local system and then append the location of where that jar file was into the Classpath. Now usually the way of doing things is much easier using build tools such as Apache Maven or Gradle, but let's just forget about those for now and consider Classpaths purely from a plain old vanilla Java point of view. So, as we said before, we have these two types of Classpath. We have the compile time Classpath. That's the Classpath which is used when we compile our Java source code using the javac tool or javac tool, that's the Java compiler, which is in the JDK. So that's the notion of the compile time Classpath. And then once we execute that javac or javac command line to take that Java file, that's our source code, so myapp.java for example, once we've done javac, myapp.java, once we've done that compilation to take that myapp.java file, and the Java compiler has compiled that source code into the corresponding bytecode using whatever classpath was given to it, this compile time classpath, then we end up with a .class file which contains the bytecode. So now we have gone from myapp.java, we've run it through the Java compiler, passing in the classpath, so it could resolve all the references in our source code. So it could resolve, for example, our import java.list, our import to org.commons.lang3 string utils, for example, from Apache Commons Lang. And then we've ended up with our myapp.class, which contains the bytecode The idea being that then this myapp.class can then be passed to the JVM, that's the Java Virtual Machine, and it can then run that class to execute our program. And this is where the notion of the runtime class path comes in. Because just like we had to provide a class path for the compiler to do its job, in other words, for the compiler to be able to locate all of the classes that we imported in our code, similarly, when we run our class using the JVM also needs to know where to find those classes that we've referenced. Because when you compile something in Java, the compiler doesn't magically take all of the snippets of code we need and somehow embed it into the bytecode. Instead, Java is what's known as dynamically linked. And that means that instead of embedding all of the snippets of code that we need inside the bytecode from the libraries that we're using, instead of that, it just expects those libraries to exist somewhere, and it can just hook in the pieces of code as it needs from wherever they're located. And wherever they're located is defined by the runtime class path. So if, for example, going with the Commons Lang idea, if you did a Google search now for Commons Lang download jar, for example, you'd end up on the website for Apache Commons, and underneath there you'd have two different types of downloads, a binaries section and a source section. The source section would be the actual source code, which we don't care about if we're just using the library, and instead we care about the binaries section, which would give us the jar file we actually use and include on our class path. And there's a file here, Commons Lang 3.3.12.0 bin.zip. That's what we'd download, and then we'd unzip that, and inside there there'd be a Commons Lang 3.3.12.0.jar file, and that single jar file is what we would pass to this class path. And we'd pass the same jar file to the compile time class path when we're compiling our source code, and to the runtime class path when we're running our compiled bytecode. In this way, it's nice and straightforward. The compiler uses the library when compiling the code, and then when running the code, the JVM can load that exact same library. Hopefully that makes sense. It's just really a question of the fact that whatever set of libraries you're compiling with, you also want to run with the same set of libraries. So that's the notion of compile time and runtime class paths. Now how you actually pass those to the Java compiler or the JVM is there's a flag -cp or -- class path, and then you just pass in either a semicolon separated list of locations, which is where your libraries are on Windows, or a colon separated list of locations where your libraries are, and that's on Linux or Mac. So this kind of looks very similar to the notion of a system path you'll see in Windows or in Linux or Mac. So for example, if you go to a DOS prompt in Windows and you type in echo space %sign path %sign enter, then you'll see your system path in front of you printed out, and you can see that that's a list of locations, in other words, of either directories or files, or folders and files if you like, which are separated by semicolons, and this is the list of all of the places where Windows would look to whenever you type a command in Windows, to be able to resolve where that command is actually located. Similarly, doing a similar thing in Linux or Mac, so if you did echo space $, and then in capitals path, enter, from a terminal session or from terminal, then you'd see a similar kind of thing. You'd see a list of directories or files, separated this time not with a semicolon, but with a colon. And that's because there's a slight difference between how files and directories are handled in Windows and how they're handled in Linux and Mac. So semicolon for Windows, colon for Mac. And to dereference, that is, get the value of that environment variable, path, which is the system path. In Windows, you surround that with %signs, and in Linux and Mac, you just prefix it with a $sign instead. So a few differences, but fundamentally, it's doing the same thing. It's an environment variable, the system path is, which describes to the system a set of directories or files to look in to resolve, that is, find the location of any command that you type in the terminal. It's a similar thing with the class path. If you look at a Java class path, for example, if you're in an IDE, like IntelliJ IDEA or Eclipse, when you run a program, you will typically see the command line which is used to run that program. So you'll see Java, or usually the big long path to Java, the exact path to it, then -cp or -- class path, and a huge set of directories or files separated by semicolon or colon, and then the fully qualified class name at the end, representing the program whose main method you're actually running. To go back to the command line though, when you compile code, you compile it with javac a space, then -cp a space, and then this set of directories or set of files, typically, which is the set of jar files you want to pass to the compiler. This is the compile time class path you're constructing now, separated by semicolons or colons, depending on your system. Incidentally, you can also not supply that and set an environment variable instead, but that's not really typical these days. And for executing a Java program using the JVM, again, it's Java -cp -class path, again, passing in now the runtime class path. Okay, so that's all well and good, and that should be clear. So now we know the compiler uses the compile time class path, the JVM uses the runtime class path. We probably have some questions. Like, for example, what happens if you try to import a class that isn't on the compile time class path, and you try and compile that class? Well, when that happens, you get compilation errors, which you've probably seen. And the IDE will oftentimes help you out with this by either underlining them in a squiggly red line or enumerating all of the errors, compilation errors, in a nice little list with these red X's. Or you'll see it, for example, when you're trying to do a Maven clean install, when it's going through the compilation phase, and it'll just give you a list of compilation errors which the JavaC compiler has found, and it'll just show you those in the terminal. So those are compilation errors. We're familiar with those as Java developers, and the way to solve those compilation errors is to ensure that the library that you're using is on the compile time class path. Now, typically we don't actually invoke the Java compiler from the command line like we described earlier on. That was just to give you background as to what actually happens behind the scenes. Instead, typically you're using a build tool such as Apache Maven or Gradle, and so when you get compilation errors, then usually you have to go back to your either pom.xml in the Apache Maven case or your build.gradle in the Gradle case, and add a so-called dependency into that build file, that build configuration file, to declare to the build tool that you want to use the library that you're referencing inside your source code. Now, normally we do it the other way around. We decide what libraries we're going to use, and then we put them into the dependencies section inside the build file. But then maybe we, grab some code off the web, and it turns out it's from an incompatible version or from an older version of that library, and then we might encounter a compilation error because we're trying to reference, for example, a method on a class which has been removed in a newer version, or we're trying to reference a class that no longer exists in that specific package because a newer version has somehow moved that class to a different package. Maybe that project's been refactored somewhat. And then we can drill in to look at the actual versions of the libraries that we're using, reference the Java doc for those versions, and do a bit of investigation work to be able to figure out what version we need to change that dependency to fix that compilation error. That's normally what happens, normally the type of compilation errors that you get in professional Java development. You can also get another type of error, an exception in this case, related to the compile time class path, and that's when you're using reflection. So when you use Java reflection to load and instantiate a class dynamically, you use a method called class.forename. That's the forename static method invoked against the class type, and to that you pass the class that you want to load at runtime. Now, because something can go wrong with this method, the class.forename method itself forces you to catch a so-called checked exception. That's when you can only invoke the method providing you surround it in a try and catch block. In other words, inside a try block you have the class.forename passing in the fully qualified class name of the thing you want to load, and then underneath that you have the catch block, which catches that so-called class not found exception and then enables you to react in whatever way you want to react to it to. So, for example, you might want to, if you're loading classes dynamically, maybe you want to log an error out to the log file to say you couldn't load a class. If it's some kind of server application, if it was some kind of widget or UI component that you'd made, maybe you want to issue a dialog to the user saying you couldn't load that class. If you were designing, for example, a Swing-based application where you've got some kind of homegrown component loading mechanism or whatever, this is a very advanced type of coding you might do, but nonetheless it's one thing that's relevant to a compile time class path. If you don't understand that, just forget about it for now. It's not that important. The main takeaway is the fact that you can get compilation errors when compiling, if the compiler can't find the classes that you're importing, or you can get a class not found exception when you're trying to load a class dynamically and that class is not found. Now, when you're actually running a Java program using the JVM, as we said before, the JVM uses the runtime class path. And sometimes when running an application with a JVM, you might encounter a no class def found error, which is run. And you'll see this, you'll be running the application and in the log file or in the terminal it'll say no class def found error with a stack trace. The stack trace in this case is going to be largely irrelevant to you because it's the low-level details of the class loading execution path, so you don't really care about that, but you do care about the fact that you've got a no class def found error. And what that means is that there's a class which is being attempted to be used during the course of running this bytecode, but that class can't be found. And usually this happens whereby something's missing off of the runtime class path, or it can also be a different version as well, but let's just consider a library is missing. So for example, going back to the commons lang library inclusion we saw earlier, if you compile your myapp.java file, which uses a specific class from commons lang, and that compilation is successful because the compiler could find all the classes, it spits out your bytecode, it spits out the myapp.class file, containing the bytecode, but then if you take that myapp.class file and you run it with the JVM, but not including that jar file, so you don't include this time the commons lang jar file, then you would 100% get a no class def found error. And that's because the JVM can't find that specific class that you're trying to load because the library is missing off of the runtime class path. So that's typically where you'd get a no class def found error. Now, as we've said, we don't do things by the command line. We use typically build tools such as Apache, Maven, or Java, and that's nice because we don't have to think in terms of which individual jar files we're including into the class path, and instead we just say what dependency we want to use. And when we pass a dependency to Maven or to Gradle, that build tool is responsible for downloading those libraries and all of the jar files those libraries might use, because usually it's not a case of one library just means we have to download one jar file. Usually libraries will build upon other libraries, and so what you actually have is like one jar file needing a set of other jar files, which in turn those jar files need another set of jar files, and that's why we don't do things on the command line constructing our own class paths, but instead we use a tool like Apache Maven or Gradle to be able to manage all that for us using these so-called dependency trees. But the great thing about these tools is that they will dynamically construct these compile time or runtime class paths for us. So for example, when you compile in Maven, then by doing Maven compile to compile your production source code, or Maven test compile to compile your test source code, then it will dynamically construct a compile time class path of all the different libraries that it requires to be able to compile what you've instructed it to compile. Similarly, if you run an application through Maven or through Gradle, it will construct a runtime class path too. Now, in reality, we don't tend to run our applications from the build tool. Instead, what we do is we use the build tool to construct or build a so-called distributable, which is the end runnable kind of unit. So that might be, for example, a WAR file which you deploy into an application server, or a standalone jar file which includes all of the classes embedded inside it, whatever it might be. Nonetheless, Maven or Gradle would construct that runtime class path and build that final distributable, that final runnable unit, if you like, using that class path. Key point here is that everything's done for you. You don't have to worry about the construction of different class paths. To a large extent, you can ignore them until things go wrong, and then, armed with the knowledge that you've had in this episode, you can investigate what's gone wrong and come up with a solution. And that might be because you have different, as we've said before, version differences, which you can investigate, or investigate if certain libraries are missing from the runtime class path, which were on the compile time class path, and such like. Now, we also touched upon briefly a second ago the notion of compiling test source code. So just as you have the production source code, for example, in a Maven project, which is inside the source main Java directory tree, you can also have your test classes. Those are the unit tests you write, integration tests, that kind of thing. And those won't be in source main Java, they will be in source test Java. And if you noticed, I may have used the phrase test class path. And we won't go too much into this, but basically, when you look, for example, inside a Maven build file, when you declare a dependency, you give the group ID, the artifact ID, and the version. That enables Maven to locate that specific library. So for example, going back to a commons lang example earlier on, the dependency might say group ID of org.apache.commons, an artifact ID might be commons-lang3, and a version might be 3.12.0. Those are the so-called GAV coordinates, standing for group ID, artifact ID, and version, which enable the build tool to refer to a very specific dependency which it needs to pull down from the web, the Maven central repository in this case. However, in addition to those three mandatory components, you also have the option to specify an optional component, which is the scope. You may have seen this before. In the build file, you may see scope. So for example, and this is where our example of the test class path comes in. If, for example, I'm using Mockito, which is a mocking library, then I would include that dependency inside the build file, but I would also include a scope tag, and I would give the value of test. And what this does is, this makes sure that that Mockito library is only ever used inside the test class path, and it's never used inside the compile time or the runtime class path. That's because there's no reason for me to include the Mockito library into my production application. In fact, I wouldn't want to do that. That would be, you only ever want to include the stuff which actually comprises your production source code itself. So any tools or utilities or frameworks used for testing and such like, you want to make sure they're not included in that final distributable, which is the thing you're going to run in production. So Maven and Gradle too have this notion of a test class path. So JUnit would be part of the test class path, Mockito would be part of a test class path, any Hamcrest matches or AssertJ or any other testing type stuff, they would be part of the test class path as well. Now, of course, your test classes also need to refer to your production classes, because in your unit tests, for example, you're going to create a production class as a so-called system under test, and you're going to write some tests against it. And to do that, you'd import that particular production class, and you'd instantiate it and use it inside that unit test code. Now, if using the test scope tag only declared just the libraries annotated with it as part of the test class path, then it means we wouldn't be able to compile our test classes because we'd have no way of including in the production classes we need. So the test class path is special in that how that's built is it's basically adding on to the existing compile time class path. So the compile class path is the default class path type in Maven, which is also used as the runtime class path, because typically what you compile against and all the libraries you use for compile time are the libraries you still want to use at runtime. So the compile time and the runtime class paths are the same if you don't include this scope tag, although it's possible to specifically declare something as compile scope or runtime scope, which is more advanced than we need to go into for this particular episode. But the key point is that when you have libraries scoped as test, it means that when Maven or Gradle is running or constructing this test class path or test compile time class path, it's taking the existing compile time class path and all the libraries which are on that, and then it's appending these other test libraries which we've called out by using this scope test tag as well. The final point to say about this is that in doing this, marking these test dependencies as test scope, it means that when Maven then creates the jar file or creates the WAR file or runs the application code or whatever, it won't include those libraries inside the runtime class path because they've been designated as test-only libraries. So, a lot to take in there if you're a beginner, but hopefully that's given you a much clearer idea of how Classpath works, the different types of class paths, the errors you might encounter, and what actually happens behind the scenes from both a low level and a build tool point of view. Now, if you're completely new to all of this and you want a helping hand to get up and running with Java, then go grab your Java Jumpstart guide completely free at javaeasily.com. And if you're interested in taking your knowledge of build tools such as Maven to the next level, then also check out the courses we have at courses.javaeasily.com. All that remains to say is have a great day, keep going with your Java journey, and I'll see you in the next episode.